Welcome to math class. Today we're going to be showing you the Pythagorean Theorem and a proof of it, not just saying like in high schoolers who just know a squared plus b squared equals c squared. They take it to be true. Many people don't see the logic behind it. So I'm going to show you some of the logic that's behind it using this proof that was done by Euclid. It's called the Bride's Chair, and if you actually go to this little link down here, there's an entire thing of this proof that I'm going to be showing you, except it's a little bit more animated. I couldn't do it because I'm using a Geometry Sketchpad. But, alright, so we have our right triangle, and by the Pythagorean Theorem way up here, we have a squared plus b squared is equal to c squared. So, we're going to make that happen. So, a squared plus b squared equals c squared. Now, in this proof, we're going to be doing something a little bit kind of weird. But by any simple algebra class, if you divide one half of the equation, you have to divide the opposite half of the equation. So here, we're going to be dividing by 2, or you can say multiply by a half. Either way, they're equivalent. And if we do it to this side, we have to do it to this side. So this is either multiplied by 1/2, or you can say it's also divided by 2. So we have 1/2 the quantity of a squared plus b squared is equal to 1/2 of c squared. So we have our squares that we just created, and we're going to actually be making something that looks, oh, there you go. It's going to look like this, because these should equal half of the entire area of c squared, and then this is the other half of c squared. That's used just to show you that it all fills in. So we're going to hide these momentarily, and to start out this proof, as we said earlier, we're taking 1/2 of a squared, and we're going to be messing around with 1/2 of b squared. So we're going to be playing with these ones. This first one we're going to be doing takes this shape. Now, the area of a triangle is 1/2 base times height. So, if we don't want to change the area of this triangle, we can't change the base, and we can't change the height. So, we're going to move this point down like that. See? Now we move. If you watch the triangle, stayed the same height, and the base is still the same. So therefore, these two areas are equivalent. So we're going to hide our first one. Alright, now we have C here. It's kind of special now. We're going to try to rotate our image 90 degrees counterclockwise. So this edge should be moved over to here. So this is what it looks like after we rotate 90 degrees. See, by tessellations, a rotation, a reflection, and a translation, they don't change the area. So this is very important. We don't want to mess around with the area. If we mess it around, then our proof is false. So what we're going to do is we're going to hide this other one, because now we have this one is equivalent to the old one. Now, this step is a little more tricky. If you look way over here, we have G. What we're going to do is we're going to make a line that's CG, and it's going to be perpendicular to AB. And the reason we do this is because if we were to draw that, we want to try to make something that's parallel to this. So since this is a square, if we want to make a line parallel to this one, we can just make perpendicular to these ones. So by clicking our next button, that's what this line here is. So by doing this, same thing we did in our first step, by moving this one over, Boom. We have AF and we have FG. And this is the equivalent of AF, AC. Now, the height never changed because it's parallel, and AF never changed because we didn't even move them. So, there's our first triangle right there, which is the same as our first one that was over here. See? They even look actually kind of close, but their shapes are a little different. So we're going to hide these ones currently, just for a minute, and we're going to do this other one. So we're going to slide this point way up there. See? Height stayed the same because these two are parallel. Base never moved. Alright, then we're going to rotate. This time it's clockwise 90 degrees because we want to go over to here. We could do it the other way, but it's just not worth it because, as we already did earlier, we have that triangle there. So we're not going to overlap them. So we're going to take our next one. See, just moved it over, rotate 90 degrees, nothing special. So we're going to hide that one. Alright, now we have this one. Now if you remember, there's that same one that we used earlier, the CG. No, these two are parallel. So, by moving this one over to here, we don't change the height of our triangle, and we never touch the base. So the base stays the same, the height stays the same. Our triangles are still going to be so you'll still have the same area. Congruent is not quite the right word we're looking for currently. So we're going to hide that triangle. Now I'm going to bring back our triangle from before. There it is. Alright, so these two. Now, off our equation, these are equal to 1/2 of 1/2 c squared. So if we were to take this area here, this one plus this one, these two shaded areas, should equal the same as c squared. So what we're going to do now is we're going to hide these just for a minute, and we are going to show this triangle. Now we're just going to move it just over to point G. Remember, point G was just that perpendicular line to FJ, or you can say it's parallel to BJ or AF. Doesn't really matter. But we're just going to move it over. Bases stayed the same. Height stayed the same because these are parallel. So we're going to hide that one. And then watch magic as we bring back our other triangles. And they fill up all of c squared. Now, we have shown that the 1/2 a squared plus 1/2 b squared is equal to 1/2 of this area here, because we were able to put in the 1/2 c squared to fill it up, because 1/2 plus 1/2 equals 1 whole. So, let me show you just some quick measurements. Pum. Magic. Alright, so just so we don't get too distracted, we're going to show our original two triangles. So DEA, which is this one here, actually, so these two, if you look at the way that the measuring tool here, just calculated all these. You can measure the area if you click on it. So that's all I did, nothing special. So we were able to see that these DEA, which popped up right here, is 21.21, and AFG 21.21. They never change size. And then the same thing happens for BJG, this one, and HBI. Sorry about going a little backwards there. Both of these two are congruent. Alright, so last step was if we add these two. So here, if you look, we did HBI plus DEA. So HBI, DEA add together equals 25.68. Kind of weird, because it's the same as our other triangle that we made, ABG. Ooh. So magically, they're both the same, both congruent, and that's actually the end of our proof. You can find other proofs here at cutttheknot.org/Pythagoras, and the Java applet done by Jim Morey can also be found at that website at this little link here. Sorry I don't have them embedded. I'm new to YouTube, but that's all that I have for you guys. Any questions, leave them in the comments, and I'll try to get to them if I'm able to. Bye-bye.